All right, we're back together. Some years I have time to get to this set of slides. Some other years I don't, but this year we do. We're doing great. So let me tell you something about stainless. I don't know how far I'll be able to go, but let's get started. Oops. Stainless steels come in many flavors. We have the ferritic stainless steels, in which all stainless steels have a lot of chromium, because chromium is what makes them stainless. But some of those have a final microstructure that is that of ferrite, some of austenite, some of a combination of both, right? Some can be martensite. Let's start talking about the stainless steels that are ferritic. And ferritic stainless steels, what they have is ferrite stabilizers. And we discussed them briefly when we were talking about the basics of carbon steels, when I said, well, some elements stabilize the ferrite. And here you go. They have these ferrite promoters or ferrite stabilizers, such as that were in these curves I showed you, like aluminum, moly, niobium, chromium, and there are others too, right? And as you get deeper and deeper, you might wonder why this and not that, right? And we start having more and more interesting conversations, because these things not only promote the ferrite, but sometimes they want to form carbides, and there's a balance between those. Because these are these steels, essentially they connect the delta ferrite with the alpha ferrite, and they do away with the gamma in between. So until you melt them, these steels are ferrite. Can you do heat treatment to them? Well, I'm saying you can't. Of course you can't, because the cool thing of the heat treatments is you get into this new phase that is austenite, the hot phase, and then when you cool down, this hot phase decomposes and gives you different microstructures with which you can play games, and will give you different mechanical properties. And what is the one problem of ferritic stainless steels, as well of aluminum and nickel and most other alloys that don't have a difference between a cold phase and a hot phase, right? They don't have this allotriomorph. What the problem is coarsening, because right next to the weld pool, you have this high temperature, and the grains get bigger and bigger and bigger. And when you cool down, they don't transform into anything. They're just big grains. So you want to use typically low heat inputs to avoid this coarsening, right? You want to avoid preheat, so you don't spend too long time at high temperatures. And the filler should match or exceed the chromium content of the alloy, because you want to make sure is ferritic. Chromium is a stabilizer of the ferrite. How about austenitics? Austenitics are the ones we know all too well, right? Like a cutlery, right? It's made of these austenitic stainless steels, typically like 18% chromium, 8% nickel, and all these variations. Those are the 300 and something series, right? 304, 302, 310, 316. And what do they have? Well, guess what? They have stabilizers of the austenite. And here we have the austenite stabilizers. Manganese, definitely nickel, right? And some case carbon, although carbon is tricky, because carbon wants to come together with the chromium or the other carbide formers. And once the chromium reacts with the carbon, is not good helping for your corrosion resistance anymore. So although stainless can have a high carbon, typically when you weld them, you want to have as low carbon as possible. Close to none would be ideal, because in welding you have these hot cycles that reach all the way to melting, that would precipitate these carbides that take away the corrosion resistance. We also mentioned how you want to forge carbon steels in the austenitic region because it's very soft. And sure enough, austenitic stainless steels, because of this crystalline, this arrangement of atoms in the crystalline lattice, is very ductile, but not very strong, right? So that's that's one of they're good for resisting. They are tough, they can resist corrosion, but they're not too strong. What problems they can have? One is sensitization, which I just discussed. You tend to put a lot of carbon to stabilize the austenite, and then the carbon wants to make friends with the chromium, and then you have no corrosion resistance and no toughness, right? Everything is wrong. The other problem is hot cracking. And I'm going to be discussing hot cracking later on because it's very interesting. So problem number one, sensitization. So this image, you get to see the austenite grain size, the austenite grains in the stainless steel. These are the austenite grains. And you see that this grain boundary is kind of thick. This one is thin here, but most of the grain boundaries are pretty thick. Look, this is thin, but this is thick here. What happened? Well, it's not that the grain boundary is thick. So we have all these carbides that precipitated at the grain boundary. Again, the grain boundaries are places of high energy. That's why things precipitate at the grain boundaries. A chromium carbide, they have this stoichiometry of chromium 23C6. We write M23 because it can be other metals that are chemically similar to chromium, right? This M23C6 or chromium 23C6, to form, they have to suck up the chromium from the matrix. And so what you get to see is in these grain boundaries that are thick, we have all these carbides, but much worse than the carbides, we have a whole channel that was depleted of chromium because the carbide sucked up all the chromium. It diffused, the chromium diffused into the chromium carbide. And this is horrible. Then corrosion would progress down these sensitized areas, and your material falls apart grain by grain. You paid for stainless steel, you got a bunch of like iron powder, right? Not good, right? What makes sensitization bad? High carbon. That's bad because you have more chances of carbides. And who has high carbon? The austenitic stainless steels, right? Bad. That's why you would buy a 304L. When you buy L means low carbon, and those are grades that are meant to be welded. Time, say you cook the things for too long time, right? You have a high heat input, or you decided you wanted to preheat. Both pretty bad ideas, because that gives time for whatever carbon you have there to react with the chromium and precipitate, right? In the heat affected zone, sometimes you cannot avoid having some of this effect, but you want to have it as narrow as you can, as small as you can, because a small area susceptible to corrosion is much better than a big area susceptible to corrosion. In this set of slides that is from our friend Bill Newell of Euroweld, we have these super cool schematics. Here we have our plates or pipes of stainless, and here we put the weld. So right next to a heat affected zone, because the funny thing in welding is we say, well, too high temperatures can cause sensitization, but in welding, you will reach melting. So you don't get away with high temperatures. What you can do is to have high temperatures in a narrow range or high temperatures for a short time, but the high temperatures, you cannot escape. And right where you have the high temperatures, you can have a sensitized area, right? And much in contrast with carbon steels, after you do the root pass, right? Here you have a root pass. What you do is a cold pass. Isn't it funny? In carbon steels, you do a hot pass. And why? We do a hot pass because the root pass, we did it with a cellulosic electrode that had hydrogen, and we wanted with a hot pass to bake off that hydrogen, and life is good. In stainless steels, we make a root pass with stainless, and then we put a cold pass. And what's the point? That we want to keep building our weld, but we don't want the heat of our second bead to cause sensitization in our root pass. So after the root, we have a cold pass, a small pass, and in this schematic, you get to see how it would sensitize a little bit of area, but we don't want this sensitized area to reach the surface. So here we have a couple of examples of what is bad, right? In this case, they say, okay, let's make a huge root. Well, if you make a huge root, that means big heat input, means slow cooling, means sensitization. And you'd have all this area. You see 2 kilojoules, right? They're like suggesting values. But you have this root pass that is too big, and you sensitize a lot. Then it says, okay, how about, let's see if I make a small root pass, but then I make it like a hot pass, as if it was carbon steel. Well, now we have all the sensitized area reaching the surface. This would be a pretty bad weld because you got some sort of a tempered bead effect, but in this case, was all for the wrong reasons. And of course, we should not take these numbers like as if they are God-given. They're just what they are. But it says, okay, how about if we do a balance in which we make a root as small as we can, but effective, and then a next pass, a cold pass as small as we can, but effective, and then we keep building. And sensitization is much less important in the filler passes than it is at the root and sometimes at the cap. These graphs here are interesting. This graph represents the thermal cycle of welding. And this other graph on the right, of which I would love to have a better one, is a TTT diagram. Typically for this, we have TTT. Would be even better to have a CCT. But of what transformation in this case? The transformation from chromium and carbon in solution in austenite, transforming into austenite with carbides, right? This is the nose that says you start transforming carbides at this region. If you remember, at high temperatures, very often, at high temperatures, the carbides would dissolve. If it's very, very high, the carbides would dissolve. So there's no transformation. Nothing bad happens at very high temperatures. At low temperatures, the diffusion is so slow that even if the carbides wanted to transform, they don't have the kinetics to transform. But there's a sweet range, right, in which between more or less 1200 degrees and 800 degrees, at which this transformation of chromium and carbon in solution into precipitated carbides, doing everything wrong for us, is happening very fast. Same principles we have been discussing for carbon steel. But in this case, we're not talking about carbon steel, and we're not talking about the composition of austenite. We're talking about precipitation of carbides. So what you want, once you have this a CCT or a TTT about the carbides, is you want your cooling rate to be so fast that you don't want to touch the nose of the curve, right? It's we're putting together all these concepts, right? And this is the reason we started talking about carbon steel. It's so useful, it's so general, but also is the foundation of so many other things we're discussing. hot cracking is the other problem we were discussing. And in every steel has sulfur and phosphorus. And of course, you can get them out. But what you don't want is to pay for the steel if you have to get them out. So we just take it. It's part of the problems of steel making. These little small amounts of sulfur and small amount of phosphorus that actually modern steel every time have less and less have a problem. Sulfur and phosphorus are not soluble on austenite. They don't like to be in austenite, but ferrite can suck up quite a bit of sulfur and phosphorus. Ferrite can, austenite cannot. So if we are solidifying, we have this molten pool of stainless steel, and it's solidifying into first, let's say, austenite. The austenite is not taking any of this sulfur and phosphorus, and as it keeps being more and more solid and more austenite, the liquid is richer and richer in sulfur and phosphorus. In the end, I'm going to have something that is pretty much solid austenite and a liquid that is pretty much all the chock full of sulfur and phosphorus, causing a low melting temperature eutectic. And all the residual stresses during welding at that point just pull it open and there is nothing resisting it. So in stainless steels, you typically want to have a primary ferrite solidification mode. If it is a austenitic stainless steel, you still want that the first thing that comes up is what is called a primary ferrite solidification mode, right? And this is aiming to try to address this issue of let's have some ferrite suck up all the sulfur and phosphorus, such that we don't have a low melting temperature eutectic, a low temperature eutectic, causing hot cracking. And we have diagrams like this, into which I'm not going to go into a lot of detail, but it says you can calculate a chromium equivalent for your steel. It's similar to the carbon equivalent, but for chromium, or a nickel equivalent, similar to the carbon equivalent, but for nickel. And it says, depends on where you fall in this diagram, you'd end up with a ferritic stainless steel, or a stainless steel that solidifies first as ferrite and then austenite, which is what you like. Or if it's stainless steel that solidifies first as austenite and then as ferrite, it's not so cool, but you can deal. Or one that is all austenite all the time, and that would be quite prone to hot cracking. And these numbers here are what they're called the ferrite numbers, right? That they're determined with a test, and say, okay, you should have a ferrite level of 4 to avoid hot cracking in many cases. Not a God-given number, but it's a practically useful number. And you would see your weld metal where it falls here, and you would hope to have more than 4. Is 3:21, so I'm going to stop here. The quiz 2 will open at 3:30 sharp, and it's going to go on for 50 minutes for almost all of you. Let's stop here, and good luck with the quiz.